Is the universe a hologram? Imagine that everything you see, feel and hear in 3 dimensions, and your perception of time in fact derives from a flat 2-dimensional field.
What the hell is that?
This may sound like something that comes from the beginning of a science fiction movie, but this is actually what physicists have theorized for decades. Could the whole universe in fact be a hologram? This is not just a wild speculation, but a theory that scientists take very seriously, even if they cannot completely understand it. The idea is that everything is just a 2-dimensional projection of the rest of the universe, and from this perspective, our 3-dimensional world is actually a hologram. If everything you see and hear is just a projection, then why does it seem real? To answer this question, physics has to find out what information the 2-dimensional fields can have. This would allow them to understand how time passes in our 3-dimensional world.
The holographic principle is the idea that the physical reality that we are familiar with in this 3D environment that we can readily access with our eyes and our equipment, this 3D reality might be sort of like a holographic projection of more fundamental information and laws that exist and operate on a thin 2-dimensional surface that bounds us, that surrounds us, perhaps way out on the edge of the observable universe. In that sense, much like a hologram is a thin piece of plastic which you illuminate it and creates a realistic image, these laws of physics and processes way out there, through the laws of physics, would create a reality that seems real, but is really just a holographic projection of the details and data and information on that distant surface.
According to Brian Greene, this is a hard idea even for physicists to fully grasp, and they are still trying to really understand in detail what this would mean.
I like to think that what we're doing in science and in human exploration more generally is revealing fundamental truths that are out there, that are really part of the fabric of reality. They're not things which our brains process and impose on the outside world in order to organize our thoughts and our perceptions. But it's very hard to justify that perspective since, of course, everything we do, everything we think is processed through our brains. So it could be that our brains simply have this wonderful ability to find patterns and organize things in a way that allow us to tell a story about what's really happening out there. But that story is just something that our brains concoct to make sense of our perceptions. That's a real possibility.
The holographic principle came out of the study of the most extraordinary objects that are known to exist in the universe, black holes. They could hold the key to unlocking the next phase of our understanding of the laws of physics.
Black holes are regions of space where an incredible amount of matter has been crushed to a very small size, giving rise to a very powerful gravitational force that is a very strong curving of space and time. Very strong gravity in the picture of general relativity corresponds to highly curved space and time. So in the vicinity of the Earth, the amount of warpage of space and time is pretty small. It's about 1 part in a billion, it turns out. And yet that is enough to keep our feet planted to the surface of the Earth. Around the sun, space-time is warped by about 1 part in a million, and that's enough to keep all the planets in orbit. But if you go near another object, like a black hole, space-time is warped really significantly near the edge of a black hole, and that gives rise to a whole host of different and very dramatic physical phenomena. So, for instance, if you go near the edge of a black hole and you stay sufficiently far away, you're fine. But if you get too close, go over what we call the event horizon, you can't escape. The gravitational pull is so powerful that no matter how strong your rocket engines, you can't get away. Even light itself can't escape.
There's a similarity of black holes and the Big Bang, so, according to Brian Greene, they're kind of the same in some deep mathematical sense. We think of the Big Bang as a moment when the entire observable universe was crushed into a very small size.
any region of space and time where the conditions are so extreme that our mathematics breaks down and prevents us from gaining, at least as of today, a complete analytic understanding of what's going on. So the two primary examples are the center of a black hole, where the powerful gravitational pull warps space and time so dramatically that even Einstein's mathematics breaks down at the center of a black hole. And similarly at the Big Bang, the entire universe, imagine that being crushed to an infinitesimal speck. The conditions are so extreme that, again, Einstein's math can't cope, and we label our inability to understand what's going on with this fancy word, singularity.
Stephen Hawking believed information that enters a black hole is lost forever. According to this idea, if you threw your smartphone across the edge of a black hole, everything you downloaded, all the information, disappears from the universe. But this seems to violate fundamental laws of physics. The problem is, there is a pretty basic law of physics which convinces scientists that information can't be destroyed. So there seems to be a tension between black holes and this issue of the information that objects have when they fall in.
When matter falls over the edge of a black hole, I wouldn't say it's destroyed. We lose it, we no longer have access to it. But that matter does affect the black hole itself in a way that we outside observers can actually measure, we can sense it. If the black hole is a certain size before a piece of matter falls in, after the matter falls in, the black hole gets a little bit bigger. The black hole's mass goes up by the amount of mass that falls in. So the mass is really transferred from outside the black hole to inside the black hole. It's not lost.
Many scientists believe that the information we see all around us is actually encoded on a big surface that surrounds us, a thin two-dimensional surface that sort of is like a hologram. Recently, researchers from Chalmers University of Technology in Sweden and MIT in the US published a mathematical discovery which describes the emergence of gravity within a so-called holographic model of the universe. Just as everyday phenomena, such as the flow of liquid, merge from the chaotic movements of individual droplets, they describe how gravity emerges from the quantum mechanical system at the microscopic level. A grand challenge in modern theoretical physics is to find a unified theory that can describe all the laws of nature within a single framework, connecting Einstein's general theory of relativity, which describes the universe on a large scale, and quantum mechanics, which describes our world at the atomic level.
There are proposals for quantum gravity, and loop quantum gravity is one approach. There are approaches based on sort of more exotic mathematical formalism, something known as topos theory, and there's an approach called dynamical triangulation. So there are a handful of ways in which people have pursued putting gravity and quantum mechanics together. One of the distinguishing features of string theory is that when you put gravity and quantum mechanics together within string theory, very naturally, with no additional work, not having to inject anything new into the mathematics, there is the capacity to also include the electromagnetic force and the nuclear forces. That just naturally happens within the string theoretic framework. So in that sense, string theory naturally unifies not just gravity and quantum mechanics. That's important, but not the only thing it does. It also puts together the other forces into the package as well.
A central problem with any quantum theory of gravity is to explain the emergence of the classical space-time geometry in some time of a more fundamental microscopic description of nature. Scientists have been working for decades to combine Einstein's theory of gravity and quantum theory. While they have a fairly good understanding of the other fundamental interactions of forces on the quantum level, gravity is problematic and cannot be integrated with quantum mechanics at very high energies using the usual framework of quantum field theory. At lesser energy levels, it is usually ignored, while for energies approaching or exceeding the Planck scale, simple ideas about space and time break down. So a new theory of quantum gravity is necessary. This new theory of quantum gravity would allow us to understand problems of very high energy and very small dimensions of space, such as the behavior of black holes and the origin of the universe.